All right, in this podcast, we're going to talk about rate laws. All right, so just to recap just a little bit, remember that a rate is the change in the concentration of reactants over time. So the change in concentration over the change in time. And it can only be determined experimentally. So that's all we can do to figure out what the rate is determine it experimentally. All right, so the relationship between the concentration of the reactants and the rate, how fast the reaction goes, is what we call the rate law. So every single reaction has its own equation that gives us the rate law. The general form of this is seen down here. So rate equals K, concentration of A, concentration of B. Okay, now this is obviously assuming A and B are both reactants. K is a constant. We're going to talk about it in just a second. And then you might have some exponents up here, and we're going to talk about those in a second. All right, so in order to determine our rate law, we have to measure the rate with different starting concentrations of the reactants. All right, just to reiterate to you again, the rate law shows us the relationship between the rate of the reaction and the concentration of the reactants. This is how we write the formula if we are using concentration. So if we have like an aqueous system and we have moles and a certain amount of liters, okay? So these are concentration brackets, that's what they mean. So that's how we write the rate if we're talking about the concentration of the reactants. If it's a gas reaction, you can actually use partial pressures instead of concentration. So partial pressures are used. The way you write it's just slightly different, so I just wanted to make sure you understood that. So when you're dealing with something that gives you partial pressures, you'll write the rate in terms of these partial pressure sub A to some exponent, partial pressure of substance B to some other exponent, okay? They will take off on the AP exam if you try to put brackets here instead of the pressures if it's a pressure reaction. All right, so K. What is K? K is called the rate constant. It has a specific value for each reaction. The actual quantitative number associated with K can only be determined experimentally. Now, understand that when we call K the rate constant, constant is kind of a relative term because K is unique for every reaction at a specific temperature. So if you change the reaction or if you change the temperature of the reaction, you just changed your value for K. All right, now let's talk about these little X and Y exponents that we have going on. This is what we call the order of the reaction. Okay, so basically for us, it can be between 0 and 2. So X and Y are always for us going to be a 0, a 1, or a 2. And what they're telling us is how the change in the concentration affects the change in rate. Okay, so let me give you an example of this. Okay, so we're just going to take this equation right here, and I'm going to make X and Y have a value. So X, we're going to put 1. Y, we're going to put 2. So that means X, reactant A, is to the first order because it has a 1, and then reactant B is second order because it has a 2. So let's say, so I'm going to write our new rate law real quick so that we don't have to remember. Okay, all right, so there's our rate law, okay? All right, now you actually would need to know K at this point, but just for our example, we're just going to explain how one affects the other. All right, so if my rate is 1 and my concentrations are all 1, okay, then you see that this ends up just being 1, right? Okay, so everybody's good with the 1, ignoring the whole K thing. Okay, so what if I doubled A? Okay, so what happens to the rate if I double A? So let's put A is going to be 2 this time, and we're still going to leave B at 1. Okay, so hopefully what you see is that our rate is going to be changed by the same factor, right? So I doubled my concentration. That meant I doubled my rate. Okay? Now, let's look at this in terms of B. So B's got the 2 up there. So if this was 1 again, but this time we changed the B to 2. All right, now you see that this gives us a 4, right? So that means that we doubled the concentration of B, and then that, because of this square, quadrupled the rate, okay? So basically, this top number, this exponent, is just telling us to what effect does the concentration of that reactant affect the rate. All right, that brings me to 2 key points here, okay? First off, you'll never see the concentration of the products in the rate law, okay? Because this is an initial rate. Initially, we only have reactants. Remember, over time, we get to equilibrium. So initial rate, only going to have reactants. And the other thing is that the order in respect to each reactant, that can only be determined experimentally. We cannot get that from an equation. We have to do experiments to do that. So in order for us to determine the orders, we're going to have to analyze experimental data. So that brings me to the different types of rate laws. So we're going to learn about 2 different types. One of them is called the differential rate law. This describes how rate is affected by concentration. Okay? The next one is called the integrated rate law. Integrated rate law tells us how concentration changes over time. Okay? Now, understand that once you find the differential rate law, you can go back and get the integrated, or if you find the integrated, you got the differential, okay? So once you figure out one of them, you know the other information. And again, the whole purpose of the rate law is to help us understand the mechanism, which is how the reaction actually happens.